And using the refractive index, the oil is 1.470 and the water is 1.33, right? So we want to determine the critical angle, right? Hello?
Yes.
Now remember the critical angle, right? So the critical angle means at the moment the reflecting light is along the interface, right? If you are larger than that, then everything will reflect. If you're smaller than that, then everything will go through, right? So here is 90 degrees. So we can write it N oil times psi 43.4 degree equal to N water times psi 90 degree, right? So therefore, okay, let me write it. So water. So using the index. Oh, we don't need this angle here. So this angle is just any angle, right? So we are looking for the critical angle. Good. Hello. 43.4 is not a critical angle. 43.4 is just an angle. Now then, what is the theta C? So psi theta C will be psi 90, where M water is 1.33, right? Psi 90 is 1. And then you divide it by NO at 1.470. So therefore, theta C will be arc psi 1.333 divided by 1.47. What is this? So I'm going to take an arc psi of that, 65.1 degree. Good.
Yes.
Now I'm going to do couple more before we move on to the next topic here. Now I'm going to do, okay, let me see whether I did number. So I just plug in the number. Right? Hello, we're talking about these two numbers here, right?
Yes.
So we want to find a percentage difference, right? They are related to the index of refractions. The speed percentage difference is related to the index of refractions. So what it is? So 2.458 plus 2.41 divided by 2. So I'm going to subtract that 2.458 minus 2.41 divided by recall. Right, you get approximately 1.97%. Now you have to multiply by 100%. Well, that will be approximately 1.97%. Right. Good. Hello.
Yes. Thank
Sounds
you for doing
good.
that.
Now then I'm gonna do the same thing, right? For the what is that? Polystyrene. Then you're gonna do the same thing, right? So I'm gonna compare this two. It's not really a physics, right? It's just the percentage difference. And that will be 1.488 minus 1.506. Remember absolute value, right? So you should have to put a plus and minus sign here. But the answer, you don't need to do that. 1.506 times 100%. So it's going to be plus and minus 1.2%. So you can calculate that. Now, then the question of what material they disperse more, diamond or polyester? Well, obviously diamond, right? Why? The diamond reflected index are much larger than the polyester. So therefore the diamond will deflect more. You got it?
Yes.
Now what we're gonna do, and this question said the angle of incidence is 66.8 degrees. So what we try to find, I want to find the angle of refraction for different light. So other works, so we want to find the angle of refraction here. Now I'm gonna draw a normal here. For the red. For the violet. Do I have violet? I don't think I have violet color. Okay, which one is, oh, violet here. Hello?
Yes.
You like my pen?
Your ruler is pretty awesome.
Okay, no one cares, you know that? Okay, now I'm gonna draw two normal here, right, basically. Now what I'm asking you, the first one, I want to find this angle for the red. Now let me call it theta r, right? And then I'm gonna find the other angle, right? That for the violet. Good. Hello?
Yes.
Now how are we gonna do that, right? So this one is one substitution, right? Now what I need to do. Now I need to find this angle here. Okay, let me see. I think I did the similar problem last time, but we did not talk about the different color, right? So here 60 degree, right? Here 60 degree. Am I right? Hello? Hello? I'm gonna concentrate on the red, right? Okay. Now, I'm gonna find this angle here. Hello? Now, how I'm gonna find this angle? I have psi 1 times psi 66.8 degree, right? Am I right? Hello?
Yes.
Equal to the reflected index of the red, right? Which is 1.662. I'm doing red right now. Times psi theta 2. Now, what is theta 2, right? This is my theta 2 right here. Good. Hello?
Yeah, I see
Yeah,
it.
so therefore, what is theta 2 equal to? So I'm going to calculate that. 66.8 psi, right? Divided by 1.662. And then I'm taking inverse psi on that. So I got 33.6 degrees. I'm going to keep maybe 4 decimal point, 2 decimal points. Hello? Now, if that's the case, then what is this angle equal to? This angle will be 90 degrees minus theta 2, right? Am I right? Hello?
Yes.
Now, which is equal to what? Okay, let me write it outside. I don't have space inside the square, the triangle. 90 degrees minus theta 2, which is equal to 56.42 degrees. Now then I need to find this angle, right? Now why I need to find that angle? The reason I need to find this angle, I want to find the angle of incidence from inside here. Am I right? Hello? That will be my theta 3, right? Am I right? Hello?
Yes.
Now, why we need theta phi, right? Because see, one I have that theta phi, I can write the n red psi theta phi equal to 1 times psi theta r. Am I right? Hello? Hello?
I thought that the red and the violet were supposed to be on opposite sides, like the angle.
No, the problem of this question is they have two pathway here. You kind of confused. I should have to draw only one path. You see what I mean? Don't worry about the violet right here. We have nothing to do with the violet.
Oh,
So the
okay.
angle between the normal and the red line will be the angle of reflections. The angle between the violet normal and the violet line will be the angle of reflection for the violet light. You understand what I'm saying? Hello?
So I'm sorry. You said that the angle of refraction between the red and the violet would be the angle of
No,
refraction.
I'm saying that the angle of reflection for the red beam will be this angle.
Oh, okay.
And the angle of reflection for the violet beam between the normal and the violet light. You got it?
So, okay. Okay, yes.
Now, then how can I find the theta phi, right? So one thing I know, I have to find this angle, right? Now, what is this angle equal to? This angle should be equal to 180 minus 60 minus 56.42. You agree with me? Hello? I'm talking about the triangle here.
Yeah, okay, yes.
Good. Now, if I'm doing that, what is this? Minus 60 plus 180. So it's 60 feet upon 560 feet upon 580 degree. So if that's the case, then what is theta phi equal to? Theta phi will be equal to 90 degree, right? Why 90 degree? This is 90 degree, right? Am I right? Hello?
Yes.
90 degree minus 60 feet upon 580, right? So which is equal to what? Plus minus 90, 26.42. So therefore, then how are we gonna find the theta r, right? Theta r. So I'm gonna substitute everything here. 1.662 psi 26.42 degree equal to 1 times psi theta r. Am I right?
Yes.
And then you're gonna take the arc side of the argument inside, right? You vary the argument inside the square bracket first, right? So what it is, psi times 1.662, and then I'm gonna inverse psi, right? 47.7 degree. Good. Hello. Hello.
Yes.
Now then, you follow my path, right? You should be able to do the violet. The only difference, you're gonna use the reflective index of the violet, right? Not red anymore. Good. Hello.
Yes.
Let me see. Now the next one will be the left side, right? So next one will be the left side. Now then I can look at it here again, right? Now here is what? 30, right? Hello. Here is 60, right? Am I right? Hello.
Yes.
Here, if this is 60, right? So if you add this up together, how much? 150, right?
Yes.
Hello? Hello?
Yes, 120.
60, 60, 60 plus 30, 150, right?
Yeah.
So therefore, the maximum reflection, I have 1 2, but not this. We are beyond 138, right? Make sense? Hello?
Yes.
You got it? We have Miller and we have lens, right? What's the difference between Miller and lens?
Mirror.
So let's say I have
reflects light.
Miller here. So if you shine some light there, and the light gonna reflect, right? They're gonna stay in the same medium. Am I right? Same medium. So if here's air, the mirror will the reflecting light is gonna stay in the air, right? You never see a mirror, the light come in, they can penetrate over. Am I right? Hello?
Yeah. Yes, sir.
Now then what is lens, right? Lens is different, right? Lens, if you have a piece of lens, so the light going in, and then they're gonna reflect. Penetrate from medium 1, from N1 to N2. Right? Am I right? Good?
Yes.
Now, then I'm gonna talk about the plane mirror first, right? So the whole idea, what we are talking about, that is the inmate formations. Now, it's all about the inmate formation, right? Now, let's say that I have a mirror here. Now, I don't know whether you learned that before, right? I remember that when I was a kid, some people would scare you, right? And they said that you're gonna cut the apple, the peel it off around the midnight, and look at the mirror in front of the candles, and you will see your future spouse, right? What she or he look like, right? You heard about that? Hello?
No, I've always heard that there's like spooks in the mirror, like ghosts.
Yeah, the spook at the mirror, right? And then the story was, if you cut the skin of the apple, right, suddenly the skin is not one piece, and you break it, and then you will see a growth inside the mirror. All right. Okay. Anyway, now what is the mirror, right? So you can look at that, right? Now, the way the mirror, the image form, right, I'm going to explain it to you right here. Now, then I'm going to do this. Now, I should use a different color. All right. Now you see, when you look at the mirror inside, right, what you see that you're gonna see actually you're gonna see what should I say? You're gonna see the image inside the mirror. Am I right?
Yes.
Yeah, something like that. Now for them. Now we're gonna define some term, right? This we call the object distance, or the distance between the mirror and the objects. It's gonna be extended to the lens. If we have a lens here, that will be also called the object distance. Here will be the inmate distance. Now di, right? Now, one thing I know about the plane mirror is di equal to do. Am I right? If you stand in front of a mirror, right, let's say 2 meters, then the image will be 4 meters inside the mirror. Right? The distance between you and your image will be 4 meters. You understand what I'm saying? Hello?
So the distance between you and the mirror is going to be the same as the distance that's
No, I'm saying that if you're standing in front of the mirror, 2 meters in front of the mirror, then your image will be 2 meters inside the mirror. The distance between the object you and the image of you will be 4 meters. Am I right?
Yes. Okay.
Now, one thing about this plane mirror, when we try to locate the image, we always say 3 things about the image, the characteristic of the image. Now, the first thing is the image is virtual or real. Now, for the mirror, right? If the object and the image in the opposite side. Now, opposite side mean that they are not in the same side, right? If you look at that, my image is in the left and the right side, my object in the left side, right? Am I right? Hello?
Yes.
So if that's the case, then the image is virtual. So therefore here, I know my image is virtual, right? Second, then you would say that the image is enlarged, diminished, or same. So for the plane mirror, they're always same, right? And you see that, hello? Right?
Yes.
And the third thing is, are they erected or are they inverted? So are they in the same orientation, right? In other words, so are they erected or inverted? They are erected, right? Am I right? Or you can say that they are same orientation of the object. Am I right? Hello?
Yes.
Right. So that's the plane mirror. Very simple, right? Plane mirror. And plane mirror is it's not that much interest on that, right? Now, what we're gonna do, and we're gonna talk about the spherical mirror here. Now we have 2 types of mirror, right? One we call the parabolic, and another one we call the spherical mirror. Now here we're gonna talk about the spherical mirror. Now what is the spherical mirror, right? Now let's say I have a sphere. Hello?
We're here.
Yeah, why much?
Yep.
Yeah, it doesn't help me to complete it this time. Ooh. Okay. Now I have a sphere, right? So if I cut a piece of sphere out, got it? Hello?
Yes.
That will look like this, right? Now if I coat some silver on the back, you know what silver, right? Or some mercury on the back, right? Then I will have a convergent mirror. Or we give a name of that, we call it a concave mirror. Now, if I coat the silver on the other side, right? Then I will have a divergent mirror. Or we call them a convex mirror. Good. Hello?
Yes, sir.
Yes.
Now, where did you see the concave mirror, right? So you probably see that now for the graphical method, we always erect a object. Now the object like this, an upward arrow, right? Hello? Hello?
Yes, sir.
Now, Then I want to show you how to find the image, right? Using the graphical method. Now keep it in mind, the way I put the object, I can put it behind the C, right? So file location, I can put it, I can put my object, right? 1 behind the C, right? 2 at C, right? Am I right? 3 between C and F. Hello? 4 at F, right? And then 5 will be in front of F. Am I right? So I have 5 locations. I can put my object in, right? And the result, they're all different. Now what I'm gonna do, I'm gonna show you I'm gonna show you how to find the image from this object behind the C. Are you there?
Yes, sir.
Now I'm gonna do this. Now the way you're gonna do that, you're gonna draw a parallel line, right? You send in the light beam. Once you hit the mirror, then what happened? I have a concave mirror. Then this light will converge. It's gonna hit the focal point. You got it? Hello?
Yes, sir.
Now another way you can draw that is, I'm gonna use the blue color. Now if you send another beam in, now this beam is I'm always use the tip of the arrow as the reference point. Easier. Now if you send the beam in and hit the vertex, right? Am I right? Hello?
Yes, right in the middle.
Now keep it in mind, I'm using the dashed line to represent the reflecting light. You understand what I mean? The solid light is the incident light, right? Dashed line represent the reflecting light. The whole idea of the graphical method is what? Locate the intersections of the reflected rays. Hello?
Yes, sir.
Now I'm gonna do the reflecting ray, right? Now if your light hitting the vertex, they're gonna reflecting out exactly the same angle. Remember that this angle here, 10 degrees, right? Hello, you see my cursor moving? Hello?
Yes, sir.
Yes,
Now
sir, it
this
is.
one is to be 10 degrees too, right? So I'm gonna draw this. The incident light waves, well, I should say wave, and then reflecting wave. You got it? Hello?
Yes.
Now, the way I'm drawing is not very good, right? Now, because see, I did not fit the scale, right? Another thing I can tell you that is, if you have a light passing through the center of curvature, right here, then it's gonna reflecting straight forward. You understand what I'm saying? Hello? Now, like I said, I did not use the ruler to measure the exactly scale, right? So all this three way, they should be falling, they should meet in the same point. So therefore, where's the image? Hello? The image will locate it at the intersection. You understand what I'm saying?
Yes.
So my image will be here. Now, then what can I tell about the image? I remember that. Are they virtual or real? Is this image real or virtual?
Virtual?
Hello? Now remember that for the plane mirror, right? The image and the object, they are in the opposite side of the mirror. They are virtual. But now I have my image in the same side of the object. So therefore they are what?
Oh, real, yeah, okay.
Okay, is this image larger or smaller? Right? Is this image upright or inverted?
Inverted.
Right? So you have to characterize the property of the image. Are you with me?
Yes, sir.
Yeah.
Now what I'm gonna do this we call it graphical method, right? But we also have an analytical method. So analytical method means I'm gonna use a Miller equations. Now this Miller equation will be same as the lens equation later. Now what is this Miller equation say? Miller equation said 1 over f equal to 1 over dO plus 1 over di. Now here, what is f? F will be this distance. Good. Now
Yep.
what is dO? dO will be the object distance. Hello? Hello?
Yes, sir.
Now then what is di? Di will be the inmate distance. Now I'm gonna put some number here, right? Approximately, so I can see whether I get the same result. Right? Now if I look at that carefully, right? So let's say my F is 10 centimeter. So what is my DO look like? My DO look like, I would say the 28 centimeter, right? Approximately. Am I right? Hello?
Yes.
You just approximately, right? Now then, how am I gonna find the DI, right? So DI will be equal to what? 1 over F minus 1 over DO, right? Move it over this side, right? Am I right? So which is equal to 1 over 10 minus 1 over 28, which is 28 minus 10 divided by 280. Am I right? Hello? Hello?
Yes, sir.
Yes, sir.
So therefore, what is DI? Don't forget to flip it around, right? So you flip it around, will be 280 divided by 18, right? So which is 15.56, or you just write 15.6. Is this location approximately 15.6? Yes, right? Hello? Hello?
Yes, sir.
Wait, Professor, I have a question.
Yes.
When you invert it, aren't you supposed to have like a negative?
I invert the mean, I take a reciprocal of it.
Oh, okay.
No, I'm just, so what DI equal to? DI equal to this. That's what I mean.
Oh, okay,
Invert.
okay.
Yeah, not negative. Now, what I'm gonna do, I'm gonna ask you to do a problem, right, from the book, from the textbook. So hold on a second, right? So I'm gonna copy over here. Log me out. Okay. Now I'm gonna
Yes,
do this,
sir.
right? Now, like I said, if you're doing online class, you got to have some tool like I have in order to show you this. Now, the parallel line coming in, then what happened? Parallel line, they're always falling on the focal point, right? Hello?
Yes.
Now, I'm gonna give you you see all those PowerPoint I put online, I put it online. They are from other textbook. And they have a couple very good table there, right? You can look at it. Now, what I have this. Am I right? Now,
Yes, sir.
then I
Yes,
have
sir.
another light coming in, hit the vertex. And the vertex just behave like a plane mirror, right? Angle of incidence equal to angle of reflections. Now, how many degrees? If I look at this, look like 21 degrees, right? Am I right? Hello?
Yes.
Now the line coming in, and then the angle below has to be a 21 degree too, right? Am I right? Hello?
Yes, sir. This should be parallel from the other one.
So what I'm saying, this angle should be equal to this angle. Now, then I said that, right? You have another way is passing through the center of curvature. They're gonna reflecting back, right? So what I'm saying, if you have a light sending in, this light aligned to the center of curvature, they're gonna reflecting back. Why? So you can think about it. I have a tangent line here, right? Am I right? So this point behave like a plane mirror again. Are you with me? Hello?
Yeah.
Yeah. Now, if you look at this V line, what can you make up your conclusion? Hello?
That it's a real image?
No, what I'm saying, this phi, what should I say? The phi reflecting light, are they forming an intersection?
Oh, they're all parallel.
Yeah, they all parallel, right? I'm drawing very nice, right? They look all parallel, right? So therefore, what happens? If you have a object sitting on the focal point of a concave mirror, then no image form. Am I right? Hello?
Yeah, because the light's
they all
not
parallel,
crossing.
right? Now we can verify that by the Miller equation, right? Remember 1 over F equal to 1 over DI plus 1 over DO, right? Am I right? Hello?
Yes, sir.
Now,
Yes,
what
sir.
is my DO equal to here? We are sitting on the focal point, right? So DO is just equal to F, right? Am I right? Hello?
Yes, sir.
So therefore, I have what? I have 1 over DI equals 0, right? Am I right? Hello?
Yes.
Then the only way the DI form is what? At infinity, right? So I mean they parallel. Make sense?
When you say DO equals F, that's only if
because see,
DI
I'm
is.
putting here's an F, right? But at the same time, I'm putting my object exactly at the F. So therefore, DO is equal to F.
Okay.
Remember that what is DO? DO will be the distance between the vertex and the location of the objects. And this, in this case, will be F, right? Am I right?
Yeah. Yes.
Yes.
Okay, right now, now what I'm asking you to do is I did behind the scene, right? I did here. And you should go home and try it, right? It's pretty fun, right? When I learned that, I remember that when I learned that I was like a 15 years old, right? I really enjoyed to draw those pictures. Now I did behind the C, I did it at F. So you should do what? You should do it at C. And here, and in front of the F, right? Are you with me?
Yes, sir.
Now, what I'm going to talk about it now is I want to talk about the convex mirror. Now, what does convex mirror look like? Convex mirror look like this. And then I'm going to draw my principal axis, the optical axis or principal axis, right? Okay, here. Good. Hello.
Yeah.
Now, what's special about a convex mirror, right? Now, the special about a convex mirror, if you have a light parallel in, now remember that I'm always have I'm gonna use the ruler to get a better measurement of my focal point, right? So 1, 2, 3, 4, 5. Now here's my focal point. Here's my C. Now I'm gonna draw a line right here too. Now, what's special about the convex mirror? So if you have a parallel line in, what happens is they're gonna diverge. Am I right? Divergent mirror, right? Am I right? Hello.
Yes.
Now they diverge. It will look like what? They look like that they're coming out from the focal point other side. So in other words, if you have a convex mirror, your F is always negative. Why negative? I'm not going to use this F here. I'm going to use the F in the other side. If I'm use the F in the other side, mean the F is negative. Are you with me?
Okay.
Yes.
It's on the opposite side of the mirror.
Yes.
Okay.
Now I'm gonna show you a drawing, right? And then I'm gonna stop. Now let's say that I'm gonna put it here. My object, I'm gonna put it here. Now let's say F is 10 centimeter, C is 20 centimeter. My DO is look like 15 centimeter. Now what I'm gonna do, I'm gonna send the light coming in parallel in, right? Now the parallel in, they're gonna diverge, right? Diverge and what? Diverge, it look like they're coming out from the focal point on the other side. You understand what I'm saying? The light will diverge, but they look like coming out from here. Good. Hello.
Yes.
Now I try to draw the dashed line, right? Now then other loo, what is the other loo? The other loo is same thing, right? If you have the light hitting the vertex, they're gonna reflecting behave like a plane mirror right here. 24 degree, right? Here. Now you see these two reflecting light, right? This one and that one, are they gonna form an intersection? Yes or no? They're not gonna form an intersection, right? Am I right? Hello?
Correct, because they're bouncing in different directions.
Exactly. So how can I locate my image? Then you're gonna extend this line to the other side. Now, when I extend this, my reflecting light for the wet reflecting light to the other side, I find the location of the intersection right here. So therefore, my image is here. Are you with me? Hello?
Yes. So since it's on the opposite side, now the image is virtual.
Exactly, right? So therefore, now I can tell you that for all convex mirror, for all, I mean for all mean that no matter where you put your object, no matter where, okay, I should write this way. Okay, give me a second. For any locations of the objects, convex mirror or divergent mirror, right? Always form virtual, smaller, and what is that? Upright, right? Image. You got it? Hello? Hello?
Yes, sir.
Yes, sir.
Now then I'm gonna, I'm sorry, I have 2 minutes overtime, right? But anyway, I'm gonna calculate that, right? Remember 1 over F equal to 1 over DO plus 1 over DI. Now then, what is this? I have one, remember that I'm using the focal point on the other side, right? Should have a negative side here. DO is 15. So therefore, 1 over DI is equal to negative 10, negative 15, right? Am I right? Hello? Hello?
Yeah.
Now that will be a negative 15 minus 10 divided by 150. So DI will be negative 150 divided by 25, right? Am I right? Hello?
Yes.
So which is negative 6. Now my question here is this look like negative 6? Yes, right? The negative mean I measure in the back on the mirror. Okay, I'm gonna stop here.